Hello, everyone. My name is Thomas. I'm going to be talking to you about data augmentation and a slightly different way to think about it than what you might encounter everywhere else. So the typical definition for data augmentation is that it's a technique to significantly increase the diversity of data in your training and test sets without collecting new data by computationally transforming examples. So there's a bunch of words here, but in essence, you take one of your data points and you transform it in various ways, computationally, rotating, changing the color, stretching in, maybe cropping, all these things you can do. And then you feed this as your new data or as new data into your model that you're training. So typically, again, in summary, you can think of data augmentation as enlarging your data set for free. However, I think that there's a better way to think about what's happening here. So I'm going to explain this with a motivating example. Let's say that you are super interested in birds and you want to build a bird classifier, something that takes a picture of a bird and then identifies what species it is. So you gather your data set by taking a bunch of pictures of birds from your backyard. Remember, this takes all day for you because you're just sitting there waiting for birds to come and then take pictures of them. Let's say you get these four bird species found in your backyard: the cardinal, the blue jay, the robin, the goldfinch. And you're proud of your work, and you set up your training pipeline, and then you train your image classification model and build it into an app and release it so that other people can enjoy understanding and learning what bird species are as well. However, people are complaining. Your model doesn't recognize right-facing birds. So you go back and you look at your data set and you understand that, oh, all the bird pictures that I took were only left-facing. Like somehow randomly that happened, but how might we fix this? Does anyone have an idea of how we might fix this problem? You can drop it in the chat. Randomly flip the training data. Train it again with the birds flipped. Okay, exactly. That is exactly right. You take all your images and you perform a left to right mirror transformation. Then you get this new data set that has right-facing birds in it. So again, will this fix the problem? And there's going to be a bunch of yes/no questions in my presentation. So I'm just establishing that the yes is celebratory and no is this shocked face. Okay, so we have majority yeses, some nos, but I'm going to just say that yes, it will work. So does anyone have an idea of why this works? Again, just drop it in the chat. Birds are symmetric, says David. Good. Because birds are still birds when you horizontally flip them, right? All right. But really, why? Why are birds still birds when you horizontally flip them? Because birds and many other animals, including humans, usually have left to right symmetry and thus are invariant under a horizontal flip. Okay, so this is an example of a real world invariance, where invariance is a property of an object that does not change upon a specific transformation. So here is a straight on picture of a cardinal, and then the next one is a flipped left to right image, and it's almost the same thing. And then this picture, I cropped it down the middle and then copied the right-hand side and flipped it and tried to combine them back into the same picture. And so it looks quite similar, right? So this proves that birds have horizontal flip invariance. So what's an example of something that is not invariant to right-left flipping? And I'll give you a hint. There's a bunch of them on screen right now. Text, exactly. Text and letters are not invariant to right-left flipping. All right, so now we're going to do some rapid fire polls here, exploring other invariances. So is a cardinal still a cardinal when it is rotated? All right, we have a bunch of yeses. Good. Is a cardinal still a cardinal when it is cropped to appear bigger? Like in the image, you crop it and it makes it bigger in the image. Yes. Okay, good. Is a cardinal still a cardinal when it is stretched? Get some no's. Okay. Mostly yeses, and it depends. Is a cardinal still a cardinal when it is shifted in frame? Yes. All right. Got a bunch of yeses. Good. So all of these things are pointing to some fundamental invariance about a property of a cardinal, right? So by supplying the model with the data augmented in these ways, we teach the model about the cardinal's rotational invariance and size invariance and aspect ratio invariance. There's an asterisk here because to a certain degree, if you stretch the cardinal too much, it wouldn't even look like a bird anymore, right? It would just be a couple pixels wide or something. As well as shifted in frame, translational invariance. Okay, so what about some more difficult ones? What if you brightened your picture, maybe to simulate there's more sunlight, it's a sunnier day? Is a cardinal still a cardinal then? Okay, get a lot of yeses, and it depends. What about you decrease the contrast of the image, and perhaps this represents like taking a picture of a bird through fog? Okay, a bunch of depends as well, and then yeses. So good. So this, again, to a certain degree, you can change the lighting and it will be still a cardinal. So I call this lighting invariance. What about when it's randomly covered up in this example? Is a cardinal still a cardinal when it is randomly covered up? All right, we're getting some no's, but mostly yeses. So again, to a certain degree, I'd say yes, a cardinal is still a cardinal when it's randomly covered up. And I named this all parts invariance because although the cardinal has a bunch of defining features in it, it doesn't need all the parts of those defining features in order for us to tell that it's a cardinal, right? If you cover up the entire tail of a cardinal, you'll still likely know that it's a cardinal, or the entire beak, or whatever. So you don't actually need all the parts to identify the bird. Okay, one last one. What if you swap the red and blue values of the picture? Is a cardinal still a cardinal then? All right, we're getting a bunch of no's and then few yeses. All right, so I would argue that no, this is not true, because to an untrained eye, this blue shifted cardinal looks a lot like a blue jay, right? Another one in your class. So cardinals don't have color invariance, right? You can't randomly change the color of your cardinal and then still expect it to be a cardinal. Yeah, someone said looks like a blue jay. Good. Okay, so before we used to think about data augmentation as enlarging your data set for free, but instead you should think of it as teaching your model about fundamental invariances in your data, labels, or classes. And you should only use augmentations that make sense for your purpose. So let's look at some other examples. You can view other problems through the same lens. So for example, let's say you're designing a text recognition model that needs to read in text from a picture, right? So we already said that the left-right mirror flipping symmetry doesn't work for text. And probably rotation doesn't work either. But in this case, text has color invariance, right? You can change the color of your sign and it'll still say the same words, as well as size and translation. And you can think of other problems like song identification and other audio data. So before there was Siri and OK Google to ask what you're listening to, there was an app called Shazam. And Shazam uses like 10 seconds of audio data in order to figure out what song you're listening to. So if you imagine designing this model, you would want to tell the model that a song is still a song when the overall volume is changed, right? So it has overall volume invariance, as well as if you add some background noise, a song is still a song when you have added background noise to it, as well as some speaker quality issues, because not all speakers are going to be the same and reproduce the songs the same. And you can imagine other things like covers or key changes or tempo increase or decrease, whether or not you want to add those to your model to teach your model about those invariances. So as well as NLP and text data, this is a little harder to think about the types of invariances that you could teach your model. But one that I thought of was maybe a he-she randomizer to introduce gender invariance. So whenever you read he or she, you just replace it randomly, 50-50 chance with he or she. And therefore, whenever the model would learn like, oh, he and she are essentially the same. You could also try to swap sentence order. But again, this is difficult to think of potential augmentations that would help you. So luckily for us, you can use math to create different augmentations with something called adversarial data augmentation. So this is using knowledge of the inner workings of the model and math to construct difficult examples for the model to further train on. So here's a picture of an example. An image classifier was trained to look at this and think it's a duck. And then a researcher made very specific noise and multiplied it by a small number so that when you added it to this picture, it ended up thinking that it's a horse, right? Even though clearly to us, this is still a duck. So I call this type of invariance weakness invariance because you're providing your model with examples to improve its weakest spots. So again, you might be thinking like, how could a model that's smart enough to believe that this is a duck then further believe that this is a horse, right? This is kind of crazy. So I have one last question for you. Is tile A the same color as tile B? We have almost equal, a bunch of no's. Now no's are overtaking it. Anthony says, I need. Yeah, okay, so this is an optical illusion. And optical illusions are a type of adversarial attack on your brain, right? So someone with the inner workings of how you see the world designed this optical illusion to try to trick you to think that A and B are different colors. So again, the idea comes back to with enough examples of optical illusions, you might learn how to recognize how they work and then not be tricked by them. And it seems like a bunch of people were not tricked by this one, but maybe not. Like maybe our brain and our vision systems are so well attuned to how they work that like learning how to unsee optical illusions would be really hard. Yeah, this is the example. If you connect them with the same color, it kind of shows you that it's the same. All right, so before I finish, I just want to show that here's some code of data augmentation that I've used personally in my projects, specifically a computer vision focused object detection for automatic scoring of a board game. Notably, I didn't want to teach it that the left-right symmetry because it had text on the tiles, so I didn't want it to learn like that symmetry or that invariance, as well as I have a audio data project that's trying to detect drum events in songs, and so here's a bunch of different augmentations for audio that I've used. Okay, again, using data augmentation teaches your model about fundamental invariances. So thanks for listening, and you can ask questions in this chat.
All right. Well, thank you very much, Thomas. If we could all give Thomas a quick round of applause, that'd be great. Okay. If there are no questions, we're going to go right into our coding groups, and your instructors will take it from there. All right. So I'm going to be opening up the breakout rooms.